she will be postdoc in the group of Thomas and I, and she's finishing her PhD in France, and she has been working on the evolution of allocation trade-off in generals. And so, well, without more delay, please.
Thank you, Christophe. Thank you, everybody, for being here. Today I'm going to share with you some of my results of my PhD thesis that I made in Lyon. So I work mainly on the trade-off and what kind of mechanism can, how trade-off can emerge from which kind of mechanism. So just to start with the same definition of what I call the trade-off. A trade-off for me is a negative relationship between threats that can arise at different levels, between population, between species, between individuals, and sometimes within an individual. There is little debate around the word trade-off because it's used for talking about two different things. So first, the negative relationship. So when I'm going to talk about trade-off, I will talk about this negative relationship between individuals in a population. But trade-off is also used to talk about the internal compromise that individuals make with their energy when they have to allocate their energy between different threats. So for me, a trade-off is this negative relationship between individuals. Okay. The main explanation for a major part of trade-off arises from the differential allocation of resources, simply because individuals have a stock of energy that they have to allocate between different threats, and they can make different allocation. Just for the blue individual, he chooses to allocate more energy to the threat 2 than the threat 1, and this is the contrary for the gray individuals. And most of the times in a population, individuals spread along this negative relationship, but sometimes we have observed individuals that are able to escape from this relationship. Some empirical observations have observed that in many mutants, like in Celligans or Drosophila melanogaster or other model organisms. And if the only explanation of trade-off or differential allocation, how this is possible for individuals to escape from this relationship. So this is the question that I try to understand during my PhD thesis. And it seems that most of the time, a regulatory system is behind the allocation of resources. And we can imagine that if an individual, like the pink one, is able to express better threat value, it's possible that thanks to mutation, he accesses a new genotype space. So here I represented classical representation of a genotype space with nodes corresponding to individuals and ages corresponding to mutation or recombination events. And the normal population is in gray here. And thanks to a mutation, a pink one can access to a new subset of the genotype and maybe express a new regulatory system that allows it and the new member of the population to express a new trade-off shape and to evolve. So during my PhD thesis, I tried to address this question in two different ways, by modeling approach and an experimental evolution in Drosophila melanogaster. And in the first place, I will talk about my modeling work. So as I was saying, many trade-offs arise from the differential allocation of resources, but this differential allocation of resources is regulated by an endocrine mechanism, which implies hormones and receptors in multicellular organisms. So we choose to use all of these ingredients to build an evolutionary model to study the evolution of trade-off shape and things like that. In my model, each individual is described by a genotype composed of genes coding for hormone and receptors. These genes code for their expression and their conformation. And all of these proteins are expressed differentially on different structure and can interact with each other. So in each individual, there are different structures that are really important. Structure 1 and 2, which are structure able to convert energy into trace value. and the storage structure that I will talk more about this just after. And so receptors are expressed on the surface of the structure 1 and 2, and hormone can bind on it. And it has different effects on the individual. So this equation describes rapidly how the model works. So here you have the equation for the concentration of hormone, free hormone. So the hormone is produced regularly by a structure production, and this production is encoded genetically. A part of this free hormone are regularly degraded, and some of the hormone will bind on the receptors and then form complex hormone receptors, and some of them disconnect from this receptor and then will be back as a free hormone in the system, and just the same for the other proteins. I only work with the stable equilibrium for all those dynamics because I was able to calculate an analytical solution only at the equilibrium. So for calculus reason, it was really simple and quicker to use that the stable equilibrium. So we only use that. And when the individuals access the equilibrium, this is dynamic. So each time state there is hormone and receptor that binds and hormone and receptor that disconnects. And each time an hormone and a receptor binds on the structure 1, for example, it opens an energetic transporter on this structure. And thanks to that, energy can enter into the structure 1 and 2. At this time, we simulated a meal for each individual, which is the same for all the individuals in the population. And this increase in nutrients will be allocated between the two structures, depending on the energetic transporter that are opened. So this is the equation for the nutrition allocation. But what is really important here is that part of nutrients enter structure 1 and 2 and became trace value, and some of the nutrients stay in the organism to maintain its homeostasis, and some of the nutrients will enter a storage structure. And actually, we had a cost linked with the storage structure, which is mainly explained by the ecology of the species. We can imagine that some migratory birds will pay an important cost in storage because they cannot carry with them a lot of fats to travel the world because it's costly. And on the contrary, cetacean species will benefit of the storage to isolate from the cold and things like that. So we studied this parameter in detail after. So each time nutrients enter the structure and then go back in the individuals, a part of it is wasted. At the end of the allocation, we obtain a combination of traits for each individual, which correspond to the phenotype of our individual. Individuals can mutate and change thanks to mutation acting on regulatory sequences and modify the concentration of the expression of hormone and receptors. And mutation can also impact the coding sequences to modify the 3D structural of the protein and then modify their interaction, their affinity between each other. And we let our population evolve under a directional selection context where the two traits were under directional selection, just like represented here. And we let them evolve during 100 generations. And here is a typical result that we obtain with our simulation. So in the first place, the population is isomorphic, so everybody is at the same place. Then, after a few generations, you can see that the population spread along an isocline, the fitness isocline. And after that, populations seem seem to express a better hormonal dynamic, and then they improve their trade value. It's not really, actually it's not the same isocline of fitness, so these individuals have better fitness than this one. And half of the time it appears on trait 1, half of the time it appears on trait 2. And then the population goes back to the bisectrice of the orthogonal plan, and it's spread along this kind of relationship. So with this model, we saw that trade-offs are able to evolve in the phenotype space. And next we ask, does it mean that the trade-off shape really evolved? And we try to characterize that because the shape of trade-off is something that could modify the expected result of evolution. As I just want to show you with this example, in these two figures, A and B, population are under the same fitness landscape with the same directional selection applied, but they spread along two different relationships. So in the first example, the trade-off is concave like that, and as you can see on this trade-off, there is an optimal position for individuals. They should stay around these points because they can express a better trade value. On the contrary, the trade-off is more convex. Extreme position on the trade-off should be favored because the individuals on these extremes should express a better trade value. So that's why we wanted to focus on the shape of trade-off and to characterize that. And to do so, we tried different techniques, and thanks to a statistical people in our lab, we were able to use orthogonal circular regression, which mainly means that we try to fit the better circle to our data for a different reason that I will explain just after, and in an orthogonal way because we did not expect that the trait 1 will have an impact on the trait 2 or vice versa. So thanks to this circle fitted, we can measure the length of the trade-off, which mainly represents the standing genetic variation in the population. We can also measure the radius of the circle, and depending on this radius, we can have an information on the curvature of the trade-off. Because if the circle fitted is really, really small, then the trade-off is really curved. Otherwise, if it's a big circle, the trade-off is almost linear. And also, thanks to this method, we can fit many different shape because the center of the circle fitted can be anywhere in the orthogonal plane. So we can obtain a convex trade-off or very different kind of shape. So thanks to this method, we obtain this kind of results. So here you can see the evolution of the trade-off shape depending on the storage cost that I just presented you earlier. We tested different storage costs for simulation. So this is the mean and the quantile for 100 simulation in each case of storage cost. And what you can see is that the length of the trade-off tends to decrease with the increase of the storage cost, and the trade-off tend to be more curved. This is the radius, so if there is a small radius, you know the circle is really small and the trade-off is really curved. So the trade-offs tend to be more curved as the storage cost increased. And we compare this result with the neutral model just to verify that selection really play a role in it, and we can see that there is a quite important difference. So what does it mean? Actually, simulation under weak storage costs, there is something I didn't tell you, is that in our model we include saturation function we assume that when people or when any organisms accumulate a very big amount of energy, it will not be able to convert all this energy into trade value in the best way. Some of it should be probably wasted for many reasons, as when you are eating very too much for Christmas or things like that. So there is this saturation function in our models. And under weak storage cost, individuals can maximize their converting by store the energy before the conversion. So because they didn't pay any cost in the storage, they can maximize their conversion of resources. And so they have a slow resource consumption and makes the trade-off linear and so more long. In the case of high storage cost, individuals have to manage between the cost linked with the storage cost and the cost with the resource consumption, and so they begin to be really smaller and curved. They are curved, and so they are less longer, because when the trade-off is really curved, individuals at the extreme of the trade-off are counter-selected, and so the trade-off becomes shorter. Then we wanted to identify if a particular hormonal system is linked to a particular trade-off shape. So we made different multivariate analysis, and it seems that is not happening in our model. What is happening is that many different hormonal systems can lead to a similar trade-off shape. Simply because there is many different ways to accelerate the resource consumption, like increase the receptor production, or increase the hormonal production, or modify the affinity. So we were not able to identify a specific pattern for the physiological involved. Voila, and this work is published in Evolution at the beginning of the years. So just to sum up, for the first model, we saw that the trade-off can evolve, that trade-offs are not necessarily linear, and the shape depends on the environmental content, like the cost of storage, and that different hormonal mechanisms can lead to similar trade-off shape. However, this modeling work made several assumptions, like individual evolving in a stable environment in terms of resource availability. Also that the hormone production is supposed to be stable, and with the arbitrary threats, which is not really realistic. So we choose to modify in the first place those parameters to make another model more realistic. So in the second model that I will present you, the resource availability will fluctuate in time. The hormone production will be environment dependent, and we study the survival and fecundity rate. So the model is really at the same architecture than the precedent one. There is just few modifications. So as you can see here, a part of the regulatory sequence is depending on the nutrients available in the environment. Hence, individuals can modulate their hormone production depending on the amount of energy that can ingest. Then the second main modification is the structure, which are not structure 1 and structure 2, but represent reproduction and survival. At each time in the dynamic process, there is some ROS that are produced, and to maintain this ROS concentration to a normal states, they have to invest in the survival regularly. On the contrary, for the reproduction structure, they can invest, and their investment will not disappear across time. They just have to invest sufficiently to achieve a threshold, and then when they reach this threshold, they can reproduce with another member in the population, and then they lost this energy to give this part of the energy to their offspring. And then all the hormonal dynamics works in the same way than presented earlier, except that we do not have an analytical solution anymore, just because of this term that are in relationship with this term which is in relationship with the environment and the availability in resources. So in this model, the hormonal dynamics is we didn't wait to the stable equilibrium to study the hormonal dynamics. So we simulated meal and nutrients are located in the two structure, and then we obtain a phenotype for each individual depending on the genotype of the individual and the environment that they encountered. We simulated different resource availability contexts with a stable one and with different kind of variabilities with different frequencies of food. Just to be clear, there is no competition in the model, but there is only the density dependence, because at each time of resource occurrence, the same amount of energy is available and have to be shared equally between all the individuals in the population. So if the population is really big, they only have a really small amount of energy at each resource occurrence. So this is our first result that we obtained with this model, and what we can see is that under the very harsh circumstances, every simulation goes to extinction. So we will not study this last context, but for the other one, the stable population are in black here, and all the simulation seems to present exactly the same pattern with the same population size across time. In other type of frequency of food presence, we obtain a different stabilization around a mean of the population size, just like we expected with a better population size when the occurrence of food is more frequent. Here I just showed. Okay, it means there is something that's missing here, but nothing big, nothing really important. Here I show you the allocation of resources between survival and reproduction across time, average for each population and for different environments. So in black there is the stable environment, and the blue ones are the fluctuating environments. And what we can see that was quite surprising for us is that the investment in survival really decreases across time, while the investment in reproduction increases significantly for the frequency for the fluctuating environments. So next, we wanted to know if there is a hormonal system behind this that was able to explain what we obtained, and we just saw that the hormonal production and the receptor production tend to increase for all the type of simulation across time. And then we look at more precisely on the receptor production on each structure, and we see that is the same pattern that we saw for the survival allocation and the reproduction survival, with an important decrease for the survival structure and an important increase on reproduction structure. So that was not really, we were not really happy with this result actually. It appears that in the context that we place our population, just increase the receptor production can allow to live a great life with no investment in the survival. And something that was really surprising for us is that we definitely expected an evolution of the link of hormone production that we put in the model, that the hormone production can be dependent on the resource availability. And this, I didn't show you the result for this parameter, but it just shows an evolution like a random walk with very big variance across time. So it appears that in our simulation, this parameter did not play a role at all, which was definitely surprising. And this result could probably just due to the fact that individuals can maintain a stable survival without investing a lot in the survival. So we can change that with some parameterization, and in the short term I will modify that, and we rerun all the jobs to see if it goes as we were expecting. So that was my modeling part work, and I also study how evolution can escape from trade-off in an empirical way in Drosophila melanogaster. Actually, Roth in 2002 observed the trade-off evolution in Grius firmus, which is a cricket that presents two different morphs naturally, just here. So a short-wing morph where individuals are not able to disperse but can reproduce well, and a long-wing morph with individuals that can disperse but are not really performant at reproduction. And it saw a trade-off evolution between different populations. It compared this trade-off between populations that were sampled from the field in black and population that evolved in laboratory during 20 years in blue. And it can identify trade-off evolution with a change in the shape and in with a change in the slope and the intercept. He did that again, but with an artificial selection also in Grius firmus, where you apply different type of artificial selection, an increase of fecundity, an increase of dispersion, and both increase of the both threads. And what they showed is that the intercept of the trade-off evolved. This is the control line and the selected line, but not the slope. So that fits perfectly one of its prediction that it made many years ago. And we wanted to challenge that, and we also wanted to study traits that are more quantitative because I don't know if it's really, you can really see here, but because of the two morphisms present in the population, individual cannot really express intermediary trait value because they are supposed to be long wing or short wing. So there is two clusters of points definitely, and they, there is no trait value, intermediate trait value. So we wanted to do that in Drosophila melanogaster, and we studied two quantitative traits: the fecundity for 24 hours and the juvenile survival. We suppose that both traits are under directional selection, because if we increase juvenile survival or fecundity, it will increase the fitness of the mother. And we choose to place them in a fitness landscape that they never encountered, where a female with the best fitness will be female that express a bad juvenile survival and bad fecundity per hour. So to do that, we start with a population, and we isolated couples in tube. They mated, and female lay eggs, and then eggs developed. Thanks to that, we were able to count the number of eggs that the female laid, and we can also count the number of emergent adults, and we can obtain a juvenile survival rate. And thanks to this combination of traits, it placed the female in the fitness landscape. And if we extend this to all the population, we can see that the pink tube female is supposed to have the better fitness because it lays a lot of eggs that were developed, so she's supposed to have the better fitness. But in our control landscape, the better one should be the blue tube female, because she's the closer to the optimum. So depending on the position of female in the fitness landscape, it attributes a fitness value for each of them, and depending on this fitness value, we form the next generation. So if the blue one is the closer to the optimum, then most of the population of the next generation will be from the blue female. So we repeated this framework during 10 generations. On 8 replicates, we study 4 replicates under this control landscape and 4 replicates under directional selection. And actually, we faced many problems with one of our blocks. We made an experimental block protocol, and we faced very different problems with the first block. Like, we have no idea why, but we have to restart the first generation 3 times because flies were dying in the tube. That's something that never happened, of course. Everybody say that for artificial selection, but voila. And at the end of our artificial selection, we faced another problem that was way more a big problem because it really impacts the survival rate of individuals. We observe a big delay in the emergence of flies, and we were definitely not able to understand what was happening. It happens in all the selective regimes. So we choose to not use the block 1 result, and to only focus on the block 2 result. So I only have 4 replicates, 2 of each selective regime. Here I show you the result in the fitness landscape for the different selective regimes. So here under directional selection, each dot corresponds to the mean fitness value for the mean trait value for a population at a generation. The white dots are the first generation, and the black triangles are the latest generation. And under directional selection, we observe an increase in both traits that we definitely don't think that happened. And then under stabilizing selection, we see an increase of the fitness because the triangles are more closer to the optimum, but it's not really clear. So we studied the evolution of the mean trait value separately, and this is the GLMM result, and we observe a clear different pattern for the stabilizing and in orange is the stabilizing selection, and in gray is the directional selection. For the juvenile survival, we can see a really clear pattern of difference. But even if we detect a significant difference in fecundity, I'm not sure that it's really important, as you can see here. So we were a little bit disturbed with this result, because at the phenotype level, we can detect small evolution between the 2 selective regimes. So we tried to understand what was happening on the genetic scale, because thanks to our protocol, we got all the pedigree information. So we could run some animal models, and we can extract the G matrix for the first 5 generations and for the latest 5 generations, and then we compare the evolution of the G matrix shapes just to clarify what we saw at the phenotype space. And actually, we identified an evolution in the shape. So we studied the shape as Jones did in the 2003 and 2008, where he compared the geometric shape by different way with the size, its shape, and its orientation. So we observed a decrease in the shape, which was expected because we were doing artificial selection, so we were forced to lose some of the genetic variances across time. We observed a change in shape, which the G matrix becomes more slim, more cigar-shaped, how we said it. And we also observe a difference in the orientation of this G matrix. But as you can see here, there is no significant difference between the 2 selective regimes, which was a little bit weird. Here I just represented you the evolution of the P matrix and in blue, but you can see it well, I'm sorry, the evolution of the G matrix. And the main result is that we really obtain a G matrix with this form, which is really weird because we were expecting, we did not expect to reduce the fecundity variance so much. So here is the fecundity and here is the juvenile survival. And well, we made different assumptions about the importance of acquisition and something like that, but I really hope that you can make some help about that result. And we didn't see a different decision at this point, just I said it, okay. Just to in a more general way, I was discussing with another student in my lab about what we can do after with the method that I developed during my PhD thesis. And something that I really wanted to do is to compare, to use the circular regression to compare the storage costs between a population, a wild population, because as the model predicted, species with high storage costs should present more curved trade-off, and species with a weak storage cost should present a linear and more long trade-off. And I hope that we can maybe verify that with empirical data. As I showed in my first model, if we consider clearly the hormonal system, we can understand how trade value can improve. And we saw in my model that with an evolution on the hormonal system, we can reduce the energy waste, and then which leads to a trade value improvement. And that was confirmed with a paper of Lind in this year, where he was regulating the insulin signaling pathway in C. elegans, and he was able to reduce the energy waste by reducing the excessive production of biosynthesis. And with this particular method of C. elegans, they are able to increase both the longevity and their fecundity. And long-term way, my model I could work on the developmental dynamic and the shape of trade-off, because we think that during an individual life, the trade-off shape could possibly evolve, because individuals have to invest their energy differently depending on the stage of their life. And maybe thanks to regulatory gene network modeling, we can make those patterns emerge and study the evolution of the hormonal system and something like that. Thank you for your attention.
Thank you very much. Right on time. If we have some people who wants to ask questions on the net, do we have some followers? Really? Wow. Okay, good. So, okay, we open for question on the net, but okay, just go on.
I'm not sure I understood why it is that in the simulations that it needed to go down to reduce one trait to nothing before it could then go back up again at a higher level. So why does it need to go to the corner?
Actually, when they evolved to express better trade value, the main evolution on the hormonal system is they managed to is it easier in the model to optimize the energy investment in one trait and to not focus on the other one with the hormonal regulation, and then to make another improvement in the hormonal system and be able to allocate in both traits, actually.
So why is it simpler to optimize when there is just one trait?
It's linked with So I didn't show you that, but that was linked with the storage cost. So this is the saturating function that I was talking about, where you can see the energetic investment and the trade value conversion. So if you allow a lot of energy, at some point it saturates. So the energy that you invest more in one trade will not be. You'll be waste some of the energy. Maybe it's just, if individuals allocate the same amount of energy at both threads, this is in gray, and if it maximizes the both, if it plays at the better place in the saturating function, clearly it is the optimal position. But if the individual chooses to allocate more energy to one thread, then definitely he loses the same amount of energy in the other parts, but the difference between trade value conversion is not the same, it's not compensated with the other one. Okay, so a simple way to do that is not to invest at all in one thread.
So what you mean is that you just go to the middle, it's not that
yeah, the better way is to go to the middle, but they are not able to do that in the first place. They managed to firstly just improve one thread, so they didn't have to make the same modification on the other structural production, actually. And so all the energy goes in the same threads, and they do not have to manage with the waste linked to this saturating function.
Does it mean that, okay, so you have this extra energy that goes to the trade, so you have more waste in fact in this trade, and the optimization is actually in limiting the waste.
Yes.
So that's okay. They cannot optimize as long as they don't have enough waste to optimize the thing. I guess that's and then it goes to so yes, I guess the optimization by minimizing the waste is actually optimizing the function of this stuff.
And then it just breaks along the line, so it ends up in one corner.
And then you find an optimal solution, and then you can use the energy for something.
Then you find a slightly optimal solution before we start in the middle and we start with digits, right? But I mean, if you lift a little bit, then you should be able to optimize a little bit, right? So shouldn't you then just continue to this part? I don't understand why you have to go all the way to the end before you can do it.
Actually, I didn't. I have the result for not all the time steps, I have the result for some of them. And I didn't know what really happened at each time step for the population. It was way
it
too
passes
big.
to the extreme, yeah?
Yeah.
But you know that it passes to the extreme because you have some of those steps.
Yes, because they stay a lot of time here before go back to the middle around.
Okay, so it might be just that it's this.
No question.
Okay, then.
Also, you create descending now?
Yes. Well, we can keep this. So, I have a question on I didn't really understand everything from the selection experiment. Can you go back to the fitness landscape? Because it seems that so basically your fitness landscape, you try to decrease both fecundity and survival, but what you observe is actually the opposite effect.
Under directional selection, yes, but I can do
that. But the directional selection is to decrease. So
no. Yes.
Yeah. Okay.
The directional selection
was to increase both.
Right.
But so why did this start from low juvenile survival? So the normal thing is on their perfect juvenile survival, right? So what did you have in a harsh environment, or what's the...
No. Classically, they did not express big great juvenile survival. Most of the larvae dies. Yeah.
Okay.
Mm.
So what you're measuring is a number okay, number at a close relative number of eggs put in the ring, yeah? But that's usually a lot higher than that.
Actually, we don't know really why, but they didn't like the experimental
Right, so it was a harsh
design.
environment. That's yeah.
But we have no idea why, because classically we use the same tubes. The big difference is just that in those tubes there are only in our experiment there were only 2 flies, whereas in classic breeding there were I don't know 100 individuals in the same tube.
And there's a number of eggs that count.
That's adult fly.
Adult fly, yes.
Adult fly.
Yeah.
So male or female.
A couple, and they didn't like that.
Even if you do that, and then the survival is normally much better. Anyway, okay, this is what you have in this under these conditions, and that's why you can select what works from. But yeah, okay, so then they adapt to the conditions.
So what you see, so what you have is you have. So the first thing, how did you make the selection gradient?
Actually, I did not choose a specific selection gradient. I choose a phenotype landscape, a phenotype fitness landscape.
It's given because these are fitness components, right?
It's something that I calculated depending on the individual's position in the landscape.
You take the maximum fecundity and then the maximum survival.
Yes.
And you start it by fecundity. So does it make no? Well, you multiply one by the other.
Yeah, but you have to, since you're in the stabilizing selection, since you're selecting for a particular value, then you have to penalize them in terms of how far away they are from this value, right? So you have to choose a function to do that, which is basically those contour lines.
Yes. Yeah, I choose that function to do that.
But for directional selection, you did not then you just let them.
One was using the one with
it was not totally an artificial selection and not totally an experimental evolution, because it worked just as modeling things work. It was thinking by modeler, and so maybe it was a bad idea, but just by chance, individuals with low fitness value could be chosen to form the next generation, as it works in many models. So we got a fitness value for females, and it was sampled in the offspring pool, depending on the fitness value of the mother, but it could be possible to sample individuals that are not expressing the better fit value in this case. And like it worked the same way for the stabilizing selection.
Yeah, so you take offspring from the phenotype of the female. So it's a family selection. But so what I wonder is, so you have nearly no genetic variation in fecundity in your.
At the beginning, we had.
Yeah, but it seems to become very rapidly vertical, and still you seem to have a response of fecundity, which is maybe as good as the response of juvenile survival.
Here, yeah.
Yeah. Which
is surprising.
It's surprising, yes. And yeah, there is no way to calculate this in terms of selection and response to selection.
I think I can do that.
Because
Okay, so then, so the idea is to look at how this trade-off curve evolve. So one result that you have is this concave.
Actually, we were not able to use our circular relation on those results because we have too many variances between individuals. So we did not at the end of the artificial selection, we did not find a negative relationship between the two traits. They are positively correlated.
Right, but in the theoretical result that you had for the fecundity and survival was that you should evolve a concave relationship. Was that what you found?
Yes, for the first model under the arbitrary traits, this is what we obtained. But we did not.
It was for the fecundity and survival that you had this result.
No.
But for arbitrary trait,
This should be the same for the fecundity and the survival. The curve trade-off should appear under high storage close to context. That's what we predicted. But
okay, but then if you have the survival and fecundity, okay, let's imagine that it's just a semi-pairous organism and you just have survival and then reproduction, right? Okay, then the fitness of an individual is simply the product between survival and fecundity, okay? And that means that if you look at it relative fitness, or okay, basically look at it on log scale, then you will have a concave function, right? And this should then lead to a contour, which means that you should distribute along that.
Along the isocline, yes.
Yeah. But this is not what we found.
No.
So why was it because of costs?
I think it's mainly due to the acquisition because we were not able to control acquisition.
Well, no, I thought about the theoretical stuff now. Yeah. So, okay,
Sorry.
In the theoretical results, we found that it should be a concave.
Yes, but people, individuals have the same amount of energy, precisely.
Of course, yeah. So, okay, and then what you're saying is that in the experimental evolution, then we did not find it, and that is, of course, because they vary like hell in position. So,
it could be an explanation.
So, one thing that surprised me is that when you expect a trade-off between survival and fecundity of the same individual, but do you expect a trade-off between the survival of the mother, the fecundity of the mother, and the survival of the young?
Actually, it's really it's measured in many species. It's the quantity-quality trade-off, of the offspring. So you cannot make an infinity number of descendants and then invest an infinity quantity in each of them to maximize their juvenile survival. And actually, the level of selection, depending on the offspring of the mother, could play a role because it was not quite the same thing. And there is also a little problem with the stimulating selection because we wanted to decrease both traits, but to maintain our selection, we needed offspring in life, alive. So we cannot really go as back as worth.
So one obvious strategy that they can play to achieve this would be to basically increase the variation in investment in adjusting, because then some will get very little and die, and those that survive will be high.
And then I will select only the good one, and that could really play.
Or if you have the problem, you may have different strategy of producing offspring during life. So you have some individuals who will start producing a lot of offspring and then decrease, while some will increase.
So in this case, I guess you can have the same.
Yes, that was some standard examples.
Sure, but that means that you will, compared to your population, you will start to select those that produce little at the start, So I will take Daphnia, for example, which is not exactly the same,
Yeah.
but they start to produce their first clutch. It's generally poor quality, small eggs and things like that. And the second, third start to be much bigger.
Yeah.
So if you start to select on those that actually give the poorest at the beginning, yeah.
We actually let 3 days for mate and lay eggs with the mate to activate oogenesis and all things like that. And we choose the best period for them to lay eggs during the 20, but only on 24 hours. I know that it's really a short time, but we cannot make it longer.
Okay, so let's do any questions from the team, and we should end with screening and